Hello and good day, everyone. Today we will be presenting San Carlos Fish Pond Project with Team 21077. A special thanks to our mentors for their support throughout the process design. The senior design team consists of Chase Wiles, Alex Gomez, Sky Benitez Trainer, Connor Casey, and Anthony Holman. The San Carlos Fish Pond Project will cover the objective of the project alongside a little background information, followed by our process design and process diagrams. A sustainability and cost effectiveness will be presented with results and simulations of calculations done to determine the feasibility of the pond. And finally, we will be discussing the conclusion along with recommendations of the pond. We will be going over each section in full detail throughout the presentation.
The purpose of this project was to design a sustainable fish pond on the San Carlos Apache tribal land. Several constraints worked against the feasibility and sustainability of this project, which include, but are not limited to, water quality, soil quality, evaporation, cost, energy consumption, and process design. With the criteria set, clear definitions were set to define what sustainable, self-sufficient, and feasible mean in the scope of this project. This will be accomplished with minimal human intervention to minimize the cost and need for maintenance. Once the feasibility analysis was completed, the team moved on to the design aspect of the project. The engineering concepts contain fluid flow, evaporation, process design, and process control. The completion of the pond provides the community with a recreational area to help educate and reconnect the youth to their culture. The team partnered with Engineers Without Borders to provide a feasible and sustainable fish pond for the Nahuatl Den Zone community, where our goal is to ensure that the pond is both feasible and self-sustaining. This community is located in San Carlos, Arizona, as presented in the title slide. The water enters the pond from a well containing 189 parts per million TDS and arsenic. The pond specifications involve a 1/4 acre pond that has a maximum depth of 7 feet. The fish in the pond will be grass carp, channel catfish, black crappie, and red deer sunfish. The plants in the pond will be cattail, water lily, and duckweed.
The block flow diagram as shown below starts with groundwater from a well already placed on site. The water will travel to a water storage tank and pumped out. The pump will allow for a flow of water to travel to the filter and then to the pond. The filter has a backwash line that will be used for irrigation purposes around the pond, as the material is non-hazardous to plants. An evaporation pond will be placed 500 feet away to decrease the accumulation of contaminants left in the water and allow for proper water concentrations. The process instrumentation device diagram shows the overall process. This new design will introduce a T-joint within the piping system to allow water to flow between the existing storage tank E3 and introduce a new storage tank E4. The new tank will incorporate a level gauge I1 and overflow siphon I2 to a drain E9 as a safety measure. With the new tank incorporated, a new pump E5 needs to be added to allow for the flow of water to the pond. The pump will be operated by a float valve I4 to control the flow of water into the pond. The filter E6 will be placed after the pump to remove 97% of arsenic from the water before it enters. A globe valve I3 will be placed on the outlet of the filter to monitor the flow of water to the pond by changing the volumetric outflow. The filter also has a backwash system built in P9. A subsurface aerator E8 will be placed at the bottom of the pond to allow oxygen to diffuse in the water, which encourages mixing and breaks down molecules. The well water contains arsenic as well as other dissolved solids that will increase in concentration in the pond over time. To control this, the pond will need to be partially drained on a yearly basis and refilled with fresh water. The water that is drained will carry away dissolved solids and have concentrated in the pond. A separate evaporation pond E11 will be placed near the northeast edge of the site to dispose the drained water to minimize the concentration levels of the fish pond and will be operated by a pump E10 to drain 1/4 of the pond yearly.
The water will come from a well on site that is treated to remove arsenic. This substantially lowers the cost to move the water into the pond. The solar-powered aerator ensures our dissolved oxygen concentration exceeds the amount we need to meet our biological oxygen demand and chemical oxygen demand. This means anything that can decompose in the pond will. The material that can't decompose in the pond will slowly leave the pond with each drain. Grass carp was added to the pond to control the algae population. Fish feed and pond fertilizer will provide adequate vitamins, nitrogen, phosphorus, and potassium levels for the fish and plants. Edible plants will ease the burden of feeding fish as plants grow and eat more. Finally, the maximum allowable arsenic levels we cannot exceed are 0.04 parts per million for arsenic and 1,000 parts per million for TDS per the Environmental Protection Agency. The accumulation of arsenic and TDS were modeled using a series of mass balances. Since TDS accumulates rapidly in the pond, we must drain a quarter of the pond annually. The charts with 3 lines indicate the concentration of the pond as a function of drains at 3 different points in time: after the drain, after refilling the pond, and after the time in between the drain. As seen by the charts on the top portion of the slides, TDS and arsenic concentration approach a steady state value. The arsenic with the drain and filter approaches a value of 0.0032 parts per million, lower than our limit of 0.04 parts per million. The TDS with the drain approaches a value of 863 parts per million, lower than our limit of 1,000 parts per million. This accounts for the worst case scenario in which we receive no rain at all, as rain does not contain arsenic or TDS and in turn lowers the concentration of the pond. The evaporation pond takes up to 1/20th of an acre. The surface area of the pond was optimized so that the evaporation pond is empty before we begin our next drain.
Convective mass transfer calculations were generated with the application of diffusion of gases using Reynolds, Schmidt, and Sherwood equations. Major assumptions in the model are that the surface film temperature is the same as the ambient air temperature, and modeling the mass transfer as 2 halves of a day, with the average high temperature for 12 hours and the average low for the night, along with the assumption that the nighttime wind velocity will be 1/4 that of the day. While the pan evaporation data was collected and scaled to the pond surface area, the precipitation data was also scaled for its contribution on the pond. The graph on the left compares the 2 methods. Since there is no significant difference between the 2 methods, they are combined to create an average mass transfer of water evaporation that is used in the graph on the right, which also includes the rainfall contribution, to yield the average daily demand in gallons of water for the pond to stay level.
A simulation of the filter was run using ETDOT. The media used was ferric iron oxide to effectively remove both arsenic 3 and arsenic 5. By EPA standards, 66% of the inlet arsenic concentration needed to be removed before reaching the pond. The results showed arsenic removal compliant with EPA standards until approximately 4.79 years later, when the media will be too full to do any further adsorption. The media should be replaced prior to this time because ions of hexavalent chromium and iron begin to displace previously adsorbed arsenic, which causes a dramatic spike in the outlet arsenic concentration. In conclusion, it is feasible to build a fish pond on the San Carlos Apache Reservation, but it will require maintenance such as draining a quarter of the pond's volume to remove harmful amounts of TDS. Additionally, the filter media must be changed every 4.79 years. A water test will be conducted twice a week, and the pond will be fertilized 3 times a year. As a precaution, pond chemicals should be stored on site to account for sudden changes in pH and turbidity. A cost breakdown is included for all of the necessities in starting the pond, with the cost totaling just over $56,000. These are our references. Thank you for taking the time to listen to our presentation.